Hi, and welcome everyone to the show. You are listening to The Cyber Riddler, a podcast that talks about offensive and defensive side of the cyber world. I'm your host, Ahmed Al-Murabi. If you are a pen tester or red teamer, you usually have two things to do. Either you use a pre-made tools or you code your own things or code your own stuff. Either of that. So if you code your own stuff, you also have two things to do. Either you do it for two reasons, mainly for either evading detection or you want to write a concept that you have in mind and you want to test it out. And in a couple of episodes, we had Pavel to the show, and we talked about user space mode, kernel space mode, and we talked about kernel callbacks and many other topics. And today we have, in continuation, we have a very special guest that I watch her videos along the years, and I also follow her on Twitter. She has a very great tips. She worked on CrowdStrike, SentinelOne, and she mainly talks about Windows internals and Windows exploitation. So she's also, I don't know, she is maybe purple team. She's mainly for the blue team, red team exploitation and defender side. And I enjoyed her last talk with OffensiveCon when she talked about some very interesting things. We try to cover it out here. And I want to welcome Yarden Shafir to the show. So very warm welcome.
Hi, thank you. Thank you for hosting me here. Very happy to join the show.
So usually because I wanted to give you a very lengthy introduction, but I was like, your introduction way more cooler than what I have to offer. So please go on.
Thank you. Yeah, my introduction is all over the place. So I'm Yarden. Right now I work for Trail of Bits as a security researcher and engineer. Previously, I worked at CrowdStrike and SentinelOne, so two EDR companies. So I was mostly focused on the defensive side. Up until a couple years ago, I was also a working circus artist. I was a pastry chef for a while. I've done all sorts of other security and non-security related jobs. Yeah, been a little bit all over the place. Besides that, like you said, I mainly focus on Windows security, offensive and defensive. I teach Windows internals classes in conferences and in other places for Winsider, together with Alex Unescu, who you might be familiar with.
So I told you your introduction is much cooler than I have in my. So Yarden, before we start, I always like to start in a light topic and then light topics, and then we just go through the much deeper topics. So let's start basics. So what is a kernel? In general, just an idea about it, since we are going to depend on this all the way.
Yeah, so in all modern operating systems, we have a split between user mode and kernel mode. User mode being the unprivileged side of things, where regular processes run, where you're very limited in what you can do. Kernel mode is the privileged mode, where we have all the core operating system things, everything that needs to access hardware, anything that needs to do very, very privileged operation. So things that run in the kernel we call generally drivers. There is nothing really special about them except for their mode of execution and the fact they're allowed to do everything. So anything running in the kernel is allowed basically full control of the machine. Not entirely true nowadays, but as a generalization, it's a good generalization. If you're in the kernel, you're allowed to do everything and anything, which does, of course, make it a very attractive target for attackers who want to own a system.
Okay, so running code in kernel mode will be something that having the highest privilege. So usually attackers try to write things in that mode, but usually when there is an exploitation, you can find you can find attackers just writing code or running code into admin mode. So when you have an admin privilege, so does that means that you are really going to the kernel mode, or you just having a process with high integrity?
So no, an admin process is still a user mode process. It's still a regular process, just one that has more rights and more privileges than other processes. Now in Windows, it does get a little bit trickier because in Windows, admin processes have all sorts of special access rights. For example, loading a driver. So an admin process can load a driver into kernel mode. So the separation, so essentially on Windows, admin to kernel is not a security boundary. So admin processes are allowed to load drivers and run code in kernel mode, but an admin process or a system level process is still a user mode process. So it's still limited in what it can do. It just has more access to ask some special things from kernel mode drivers and the kernel itself.
So it's not like having admin right will be give you something that you can write directly to the kernel. You still have your boundaries in there, since it's still a user space mode. Is that correct?
Yes, admin processes still run in user space. They just have more access rights, and the boundaries become a little bit blurry, which is more of a corporate decision than a technical question.
Yeah, because usually you can see in even reteam operations or pen tester, he just want or she will just want to just access or have a admin privilege, and he will call it a day. He'll be like having a very good access, and then he will try to do either lateral movement or something. But you cannot see people like talking about like kernel exploit for some sort of exploits that use kernel mode for it. With that being said, so usually if I want to write something or I want something or my code to be running in kernel, I have to load a driver.
Yes. Now, a driver is just a piece of code that runs in kernel mode. There are good reasons for attackers to not necessarily load a driver, and we'll talk about the reasons. It did get a lot harder recently to load your own custom driver into kernel mode, but even besides that, not every attacker needs to be in kernel mode. In a lot of cases, reaching an admin process or a system process is definitely enough. It is a lot harder to hide in kernel mode. It's a slightly more visible place. People look for things in kernel mode. Also, if you have an error in kernel mode, you're going to blue screen the machine, which is very, very visible. If you blue screen a machine, someone is
Which
going
I
to
did a
know it.
lot.
Which I do a lot because that is part of my job. But if you're an attacker trying to stay hidden, blue screening a machine is one of the worst things you can do because that is practically an immediate detection. You blue screen a machine, someone is going to come and take a look and figure out what happened. And then you burnt your O days, you burnt your malware. So you did make yourself very visible. Coding for kernel mode is not all that easy, something I'm sure Pavel talked about when he was here. It is trickier to get proper kernel mode code that won't cause issues, that won't cause faults, that won't crash the machine. So a lot of attackers choose to just avoid it and not take the risk, because in user mode you can swallow errors a lot more easily. And in a way, even though user space is where we have all our processes and where the user looks for things, it is easier to hide in user mode than it is in kernel mode. So it really depends on the attacker. Some attackers do need to have a driver to monitor the system to protect their user mode processes and things like that. Some attackers, depending on what they're after, don't necessarily need to load kernel mode code. It might be safer for them not to.
And so you writing a code or developing a kernel driver, is it something like easier in a sense that is it like an easy coding style, like you are doing a normal class or you writing a normal application, or it will be requiring a different coding style or different code that should be running in memory?
Um, it is different. There are different APIs. There are also different restrictions. You are a lot more limited in kernel mode based on what APIs are available, what resources you can access, what modes of execution you have. So kernel mode is a more restrictive environment where it is harder to code for kernel mode, or at least different. I don't know if harder. And a lot more can go wrong, and anything that goes wrong immediately crashes the machine, so the stakes are higher. So you can't just easily convert code from user mode code to kernel mode code because there's a lot of different considerations and APIs, and certain resources just aren't available for kernel drivers. Some things can only be accessed from user mode because of the way they're implemented in the system.
And if I write something like if I write the driver now to like Windows driver, does that make difference? Makes difference like if in different Windows builds, like different. So if I write something like a driver, does that in a few versions in Windows, does that reflect any error or anything, or it be the same running the same?
So it really depends what versions of Windows. Generally, Windows tends to be very backwards compatible, which means if you run a driver for Windows 7, you can usually run it on Windows 8 and 8.1 and 10 and 11. But if you wrote a driver for Windows 11, you can't necessarily load it on Windows 7 and definitely not on earlier builds. Things get added, things get deprecated, certain functions don't exist or are not supported anymore. Or if you've used a function that was only added in Windows 10, a Windows 7 system won't know what to do with it. It wouldn't work. If you're lucky, the driver wouldn't load at all. If you're unlucky, the driver will crash the system immediately. So there are different considerations between different builds. Now, that also exists in user mode, but it does exist a little bit more in kernel mode, at least in the basic sense. So there are different builds, at least slightly, especially between Windows 7 and Windows 10 and 11 systems. So developers do need to be aware of that, and generally there's just a lot of checks in the driver itself, checking for different builds and choosing different code paths, or slightly different code paths or different APIs, depending on which system they're running on and which capabilities it has.
So is it easy to just load the driver? So because you can see a lot of tutorials of how to write a kernel driver, is it easy to load it on a normal Windows operating system? Because as you mentioned, I know that Windows is a big believer of compatibility, and then they just make and with that being said, you can see many things that can go wrong. That drivers or even some exploitation, some errors, some error handling that you could see, but it will not reflect the real scenario, because maybe there are some mitigation in Windows 10 or Windows 11 that you didn't see or the developer didn't know about, or in previous Windows versions. So in a sense, writing a kernel driver, is it easy to be loaded into a system?
So writing a kernel driver is easy. Writing a good kernel driver is not. And loading it into a system is a whole other question, because since Windows Vista, which has been 20 years at this point, you can't load a driver on Windows unless it's signed. Now, getting a code signature used to be a lot easier than it is now. Nowadays, it is harder than it used to be. You do need to get a code signature, whether that is by getting a legitimate one, or using a leaked one, or using a stolen one, or finding some bug in the signing mechanism, all of which has happened. But you do need to sign your driver somehow in order to load it, unless you boot your system in a special state. Now, since Windows 10, I don't remember what Windows 10 build started that, but since Windows 10, Microsoft did change the signature requirements to not allow really, really, really old drivers, because up until that point, if you had a driver that was signed, and it doesn't matter when it was signed, whether it was signed in 2004 or whether it was signed in 2020, if you had a signed driver, you could load it on a system, which means you could load any driver that has ever been signed for Windows, which caused major security issues. So with Windows 10, Microsoft did come up with a new signing scheme called WCL, the Windows hardware compatibility layer signature. So that is a new signature type. It is harder to get, so not just anyone can get a code signature. So they did restrict old drivers. So old drivers, you can set your system to enforce WCL signing, so old drivers won't load anymore. So loading a driver isn't necessarily all that easy. It has to be signed. It has to be signed with the right signature. And nowadays, there's also ways to block malicious or vulnerable drivers, or certain ones at least, from loading on a system. Technically, all you need to do to load a driver is to create a service and ask the system to start that service. But if the driver is not signed correctly, it will not load on a system. Now, that doesn't mean there's no problematic drivers out there that are signed. There's plenty of them. But still, you can't just go compile your driver unsigned, not checked, not validated, not anything, and load it on any system the way you used to.
So a better approach here, you can just take your rootkit or file your driver and give it to Microsoft to sign it for you.
Yes.
So at least you can just make but I don't know if Microsoft will sign our rootkit. I don't know. So with that, you can just go with the more vulnerable drivers who exist out there, and then you can just load it and exploit it from there.
Microsoft has signed rootkits. Microsoft still does sign rootkits. I don't know if it'll sign your rootkit personally. You'd have to ask them and see what they say. But they do accidentally sign rootkits all the time. There's been quite a lot of those the past couple of years. But yes, if you don't want to go through the trouble of having Microsoft sign your own rootkit for you, or using a leaked or stolen certificate, you can also just use a driver that is known to have vulnerabilities. Or not known. Maybe you found your own vulnerable driver and haven't told anyone about it yet. But you can use any driver that is signed properly, that has security vulnerabilities, and just exploit those security vulnerabilities to do anything to the system, to overwrite protected variables, to maybe run your own kernel shellcode if you can make that happen, depending on what driver you have, what vulnerability you have. So there's loads and loads and loads of drivers out there with security vulnerabilities. A lot of them are hardware drivers. There's been a lot of different security vulnerabilities in all sorts of different hardware drivers, and also other ones. The best case scenario for an attacker is that a vulnerable driver is already loaded on a system, and then the attacker can just go and exploit that vulnerability. But even if that driver is not already loaded on a system, the attacker, assuming they have admin rights, you do need admin rights for that, can bring a vulnerable driver along with them, drop it on a system, install it, load it into the kernel, and then that driver, which loads just fine, is now running in the kernel, and the attacker can exploit whatever vulnerability they have in that driver to attack the system and elevate themselves to kernel privileges one way or another. That technique is known as bring your own vulnerable driver. It's getting a lot of attention the past year or so. There is a public project called LOL drivers, or living off the land drivers, that has a few hundred vulnerable drivers just on GitHub for anybody to look at, use. And pretty much every week there's a new write-up or blog post about some new vulnerable driver that is being found.
So I have a question here. Usually, if there is a vulnerable driver and I try to load my driver or malicious driver to that vulnerable driver, and that driver require a security descriptor to run as an admin, does this really a security vulnerability? Because you can see that many security bugs that's been discovered, and then when they say, or the authors say, you have to have an admin privilege, it will not be considered as security vulnerability. So does this, from a security, if the vulnerable driver have a security descriptor to it, does this consider to be a security vulnerability or not?
So this is more of a question of corporate politics than it is a technical question. If you ask Microsoft, it will not be classified as a security vulnerability. You will not get a CVE for it. It will not be considered for a bug bounty, because according to Microsoft, in their philosophy, which does have its own origins and backgrounds, admin to kernel is not a boundary. So if you have a kernel vulnerability, that can only be triggered or exploited by an admin process, then no, it will not be considered a security vulnerability. Now, whether or not they're going to fix it or they're going to mitigate against it, that is a different question. Because even though for their own reasons they don't consider exploitation by an admin a security boundary, they do still try to mitigate against that, because in reality, attackers do manage to get admin rights fairly easily in a lot of cases, and they do advance from there to kernel exploitation, and that is an issue for customers. It is a security issue, even if it's not, even if it doesn't fall under their security boundary terms. So they do have mitigations against that, and they do try to go at least to adminless mode sometime in the future. And in some cases, they will even fix bugs that can only be triggered by an admin, but that really depends on the specific circumstances, if they've seen that exploited in the wild, how much public attention did the issue receive. So from a security perspective, it still is an issue, especially when for a bring your own vulnerable driver technique, you do already have to be an admin, because only admin processes can load drivers. So if you're going to drop a driver on a system and load it, you do already have to be an admin. Yeah, so it doesn't matter what the security descriptor says. You have to be an admin anyway just to load the driver. And Microsoft is trying to enforce mitigations against bring your own vulnerable drivers attacks. So they do actually see that as an issue, but you will not get a CVE, you will not get any kind of public recognitions from Microsoft or other vendors for that. So it kind of falls in this gray area.
And with the vulnerable drivers, you can see that Microsoft have an HVCI that have like a block or a list of hashes or for vulnerable drivers or for things, so they can try to block you in case you want to load a driver. But I think I think you said that in your last conference that maybe will be easier to bypass, since it's not an updated list, and you can see it's not an updated list, and you can see people just bypassing this using other modules.
Yeah, so Microsoft does have some very good security features based in their hypervisor, Hyper-V. So HVCI being one of them. HVCI stands for Hypervisor-Based Code Integrity. It's a component that uses the hypervisor to make sure everything that runs in kernel mode is what Microsoft expects to run in kernel mode, meaning you can't have any dynamic code, you can't have read, write, execute memory in the kernel, and you can't load drivers that are not signed properly. So this means that you can't load unsigned drivers at all. Even all the bypasses that existed for previous signature requirements won't work against HVCI. So a lot of bypasses existed before to still run unsigned code in the kernel. Those will not work anymore against HVCI. And also HVCI brings with it a vulnerable driver list, or a block list. It's a list that HVCI will check every time a driver tries to load to see if this driver should or shouldn't be allowed to load. So that driver that list blocks malicious and vulnerable drivers based on either their hash or their signature. So for example, if there is a signature that was stolen, or Microsoft accidentally signed some kernel rootkit, that signature might now be added to the block list. So anything signed with that signature will be blocked, or certain drivers signed with that signature will be blocked. So Microsoft does have the capability to block a lot of malicious and vulnerable drivers. Now that list doesn't block everything for a few reasons. First of all, defense always moves slower than offense. Attackers always move faster than defenders because they don't really have the same considerations. Microsoft is a huge system, billions of machines. They do need to do very, very thorough checks before they block drivers, because if they block a driver that is essential for customers, now customers can't use their machines, now systems are unusable, and that creates a huge problem. That is not really an issue that attackers have. Also, let's say there is a new vulnerable driver. Let's say you have some computer that has a vulnerable hardware driver on it. Microsoft can't go and block that vulnerable driver until there is a new version of that driver that was fixed by the vendor and that was shipped to all machines. You can't just block your network card driver. You won't be able to have any network access. We can't just go and block your graphics driver or your graphics card stops working. So unless there is a new and updated version of that problematic driver, Microsoft can't just go and block it blindly. And also, yes, there's only two releases, two updates of the block list every year, which means any new problematic driver that is discovered between those two releases in the 6 months between one release and the other will take at least a few months to be added and to be shipped. So there's always a time gap there. And sometimes it's a huge corporate, processes are slow, things get dropped, so things don't always make it to the block list when they should. And yes, there's hundreds and hundreds of known, vulnerable, and sometimes flat-out malicious drivers that are not blocked by the block list. So the block list is much better than what we used to have, which is nothing. So it is a pretty major improvement, but it doesn't fix all the problems. It doesn't block all the problematic drivers out there.
So with that being said, so where the EDR companies stand? So they detect all of these operations, and because understanding the kernel, understanding the kernel driver aspect, usually, and correct me here if I'm wrong, because what I understand is that usually in the past, companies or security companies usually had to have a driver, and then they have like user space hooks that they can control, and then these user space applications can just call an IOCTL on a kernel driver, and they can just share information to it. Now, when you just start to write codes in kernel space mode and try to do all of this operation, does all of these get detected? I don't know if ETW will share also this information or not. I don't know. But where's EDR standpoint?
So EDRs are kind of where they've always been with trying to detect malicious behaviors. Now, those malicious behaviors can be in user mode or they can be in kernel mode. EDRs do try to, let's call it, extend the HVCI block list by having their own detections on every driver that gets loaded. So, for example, EDRs can move faster than Microsoft and have their own constantly updated lists of hashes of vulnerable or malicious drivers. And every time a driver loads, they can check against their own list and choose to block that driver. Now, there's no easy way to block a driver from loading, except for during boot through a separate mechanism called ELAM. But while the machine is running, there's no easy way. There's no built-in way to block a driver from loading. EDRs each have their own different tricks for doing that. So they do have the advantage over Microsoft of being able to constantly ship new lists that they'll check against. Lists of hashes, signatures, any sort of thing they choose to look at. But also, as always, they look at behaviors, they look at suspicious behaviors, and there's the constant challenge between reliability and between detection. You don't want to have too many false positives, you don't want to have too many false negatives. So every EDR shifts the balance based on their comfort point and their customers. But EDRs do definitely supplement HVCI and the built-in Microsoft mitigations in that way. Usually they do try to detect problematic drivers before they load, because once something is already loaded in the kernel, it's already there. It's already owned the machine, so to speak. So you do really want to detect it as early as possible before it makes it to the kernel, though there are ways to detect weird or unexpected behaviors after something has loaded too.
Okay, so what are like the major mitigation that Microsoft introduced to just try to block malicious drivers along the years? Just the general mitigations.
So the biggest one is HVCI and the HVCI block list. That is really the most significant one. There are also other hypervisor-based mitigations meant to help protect third-party drivers from being messed with by a kernel exploit. Things like kernel data protection, KDP, that allows a driver to ask the hypervisor to make some of its memory read-only, whether that's static or dynamic memory. So nobody can go and change configuration. Nobody can go and change kernel variables. There's also another mitigation that is going to ship in the next version. So it hasn't shipped yet. It's still being worked on, which is not leaking kernel pointers anymore. So for many, many, many years, until this day actually, there's been a lot of APIs that have leaked kernel pointers. They have leaked the base addresses of all the kernel drivers. They have leaked the addresses of kernel objects. They've leaked a lot of different information. And having kernel pointers is really important if you're going to try to exploit the kernel, because if you're going to try to overwrite a variable or to overflow something or to write a kernel shellcode, you do need to know what is the target of your attack. You're going to need to know which address you're going to read, which address you're going to write. So you do need to leak those addresses somewhere. Now, many, many years ago, all kernel addresses were fixed, which means, let's say, the kernel binary would load in the exact same address every single time. Now, that hasn't been the case in a while with kernel ASLR, address space load randomization, or layout randomization. So now everything has a different address. The kernel has a different address, all the drivers, the pools, everything. So leaking those addresses is pretty much necessary for kernel exploitation. And until today, there's a lot of APIs that leak those addresses to almost anybody who will ask for it. But starting the next build, Microsoft is shipping a mitigation where only admin processes will be able to get kernel addresses with these APIs. And even those admin processes need to enable a special privilege called debug privilege in order to get those. So regular processes can't leak kernel addresses, and even admin processes, unless they enable debug privilege, can't leak addresses. So even if you manage to inject a shellcode into an admin process, you won't necessarily be able to get everything you need to exploit a kernel driver. So there's some really interesting additions there. With another one that is still not really implemented yet, still not shipped yet, but Dave Weston mentioned it in his Blue Hat IL talk this year, which is adminless mode, where Microsoft is just trying to move to a mode where most things will not run as admin to really enforce that security boundary, so attackers won't really be able to run as admin anymore, or not as easily anyway, to limit access to privileged resources, access to the kernel, etc.
So I think there are a couple of exploits that usually the remote code execution vulnerabilities, like in SMB, some of the SMP, like all SMP goes or Eternal Blue, or I think some of them leaking. So to be exploited, you have to leak some kernel addresses in order for you to exploit or gain system privilege. Is that correct?
In some of them, yes. In some of them were logic vulnerabilities, or vulnerabilities where, for example, you can remotely drop a DLL on disk and get some privileged process to load it. So in some cases, you did need to leak kernel addresses. In some bug classes, you don't.
Okay. So go ahead.
Oh, mostly you will need kernel addresses if you're trying to exploit a memory bug. So an arbitrary write or an arbitrary read or a buffer overflow. If you've got a logic vulnerability, then usually you won't need any kernel addresses because you're not dealing directly with memory. You're just abusing some unexpected capability, like dropping a DLL and getting some privileged process to load it, like what has happened in a few print spooler vulnerabilities recently.
Okay, so since we talked about vulnerabilities, can you recall any vulnerability that caught your attention or exploitation that caught your attention from the way it got exploited or the innovative way of this vulnerability got exploited? Anything you recall?
Let's see, which ones were there? I can't really think of a specific one. I am personally a fan of logic vulnerabilities. I don't really enjoy memory vulnerabilities. I don't like counting bytes and calculating overflows and things like that. So I do really like logic vulnerabilities, like the print spooler ones, like different drivers that just had some interesting functionalities, like allowing anyone to run a kernel shellcode, allowing anyone to open very privileged handles to anything. I don't remember which attack that was. That's been a few years ago, but personally, I'm just a fan of logic vulnerabilities instead of memory vulnerabilities, even though memory vulnerabilities do tend to be a lot more common.
But with the amount of vulnerabilities we can see, it's hard to keep up with different vulnerabilities coming out. Like before yesterday, I saw that WinRAR had a remote code execution. I don't know what's that, or is it like really a remote code execution, or a user have to click and extract the file from WinRAR to be able to trigger it. So you cannot keep up.
Honestly, I'm not sure about the details of that specific WinRAR vulnerability, because like everyone else, I can't keep up with everything. I have heard about the new WinRAR issue, but I don't really know any details because I haven't had the time to look into it.
Exactly.
You'll never completely keep up with anything. There's no use trying to be on top of everything all the time. Nobody is. We all have our niche. We all have our areas. We all have our endless lists of blog posts and papers and disclosures that we need to read and never get to. That's just what the field is. The field is very large. There's always something happening. There's always going to be something that you're going to miss, but in a lot of cases, a lot of those are the same. One vulnerability is not all that different from another. And unless it's one that is really critical or really major or exploited all over, like I think the most recent one that was really, really well known is Move It, because it's just everywhere. But there's really no need to keep up with every single vulnerability. No one can do that. And usually they come and go. There's going to be something new every day. So just focus on whatever it is that you find either interesting or relevant or useful. And we're all just doing our best.
I can't tell you how many times I saved tweets and papers to be read later, and till now I didn't, like, it's almost a year or 2 years ago. Until now, I cannot keep up with amount of papers that the security community is just publishing every day, whether it's a tweet or a concept that they proposed, and you want to sometimes there is a concept and you want to code it yourself, but even though you read it, you read the article, but you don't have the time to just implement it, and once you do, maybe this technique will be obsolete. So that's the problem of having these kind of things. So shifting the talk from like kernel space or kernel vulnerabilities to the talk you did earlier, I think 2 months ago in Offensive Con. I think you talked about a concept or thing that I didn't see before. When I heard it from your talk, I went there to search a little bit about it. It's about the Intel CET. Um, and how you can just when there is how the CPU just create a shadow stack, just and have all the return addresses to it, and then it just replicate whatever happened in the real stack in the return address. So can you talk more about this?
Yeah, absolutely. So
Kudos
CT,
for that talk. I liked it.
thank you. Yeah, so Intel CET, and there is also an equivalent in AMD on new CPUs, is the latest in the control flow initiative, in the control flow integrity initiative, which is basically a fancy way to say make sure your code does what your code intended to do, that nobody overwrote any function pointers, that nobody overwrote the return address, that nobody overwrote jump targets, that no one redirected some piece of code to run something that was not intended, usually a shellcode. So CT is a feature that was a work in progress for about a decade until it finally shipped. It's a hardware feature that makes sure that when your code returns from a function, it returns to where it meant to go. So it returned back to where it came from, instead of returning to some completely arbitrary location because somebody went and overwrote the return address on the stack. So the way CT works is that the CPU now has two stacks. One is the regular stack that has all the things a regular stack always has. And the second one is a shadow stack that is managed separately and that only has the return addresses. So when a call instruction happens, when your code calls into a function, the return address is pushed to the regular stack and also to the shadow stack. And the shadow stack, a process cannot overwrite its own shadow stack. Only the kernel can overwrite a process shadow stack. And whenever the function returns, the CPU will compare the two shadow stacks and see if the return address on the CPU will compare the two stacks and check if the return address on the regular stack is the same as the return address on the shadow stack. If they don't match, then an exception, not an exception,
Interrupt, I think.
an interrupt happens. Yes, sorry. An interrupt happens. The kernel will catch that interrupt and decide whether or not that code should be allowed to run, depending on the process, the configuration, and all sorts of different edge cases that can happen. There's also kernel CT, in which we do the exact same thing, but for kernel code. Then we use the hypervisor and the secure kernel to protect the shadow stack. So even if you have a kernel exploit, you can't just go and overwrite return addresses and redirect execution. So CT is a mitigation against an attack technique called ROP, Return-Oriented Programming, which was popular for a while. You don't really see it all that much nowadays. And CT only shipped a couple of years ago, in, I believe it was late 2020, maybe. So most people still don't have CT-compatible CPUs, but they're starting to become more common. And CT is an interesting mitigation. It does block a pretty major attack surface that there was no software mitigation for. But of course, CT does have its own bypasses, just like anything else. I did mention one of them in the offensive con talk you mentioned. And just like any other mitigation, the biggest bypass against CT is either incompatible hardware or incompatible processes and drivers. Everything needs to be compiled with CT support. And if something is not compiled with CT compatibility, then CT will not be enforced in that process or driver, which is going to be the biggest bypass, just like any mitigation.
Because it's good that you mentioned the compatibility issue, because since we told that Microsoft is a big believer of compatibility, so maybe there are some developers or some code or older code that doesn't code with CET in mind. So maybe that time will be just will not, the shadow stack will not have anything, and we will just get the interrupt again. But I don't think it will crash the application, since the application, it will not be interrupted.
So even if the CPU doesn't care if your application supports or doesn't support CT. That's a Windows thing. The CPU will push the return address to both the regular stack and the shadow stack regardless. But if those return addresses don't match and your process is not compiled with CT support, then the kernel will go and patch that issue and just let your code keep running to the modified return address, because maybe you had a good reason, maybe you changed your own return address for whatever reason. Maybe your code was written before CET, or it was not aware of CET, and for whatever design choices you made, you chose to change your own return address and redirect your code somewhere else. We don't know, we can't know. So the kernel will go and patch the issue and allow you to run to your new target. Now, judging by other mitigations like ASLR, like CFG, and how long it took developers and it took applications to start enabling them, it should be around a decade until CET is really widely adopted by developers. That's about how long it took with other mitigations that required changing compilation flags.
Do you think like Microsoft will enforce this in the future? Like when there is a code getting developed, they have to be CET compatible. Since other developers don't like think about these security issues, and they just want their code to be plugged and run immediately.
If they're going to enforce it on everything, probably not. That's not their style. That's not their philosophy. I can't think of a mitigation where they enforced it on everything. Not even today. So no, I don't think so.
I think guys. I think you should immediately see this talk. The talk about for the offensive con. I know that you guys maybe you have to repeat it 2-3 times until you get every point that Yarden talked about. So I think we covered it all. So any final thoughts you have, Yarden? For red teamers, for exploit developers, you name it.
Yeah, I do. I've done more defense work, but I do really enjoy offensive work. Look at what's on the machine. There's always older code, older applications, older drivers. The older they are, the more vulnerabilities they probably have, and the less mitigations they probably have. So take a look at what's on the machine. Take a look at what you can bring with you on the machine, even though using what's already there is always better. And you're probably going to find something, especially on older systems or systems running more third-party code or just older applications, drivers, hardware, etc.
With that being said, thank you, Yarden, for being here in the show. And I think, guys, if you have any question or anything regarding this episode, you can reach out to me or reach out to Yarden. She's very responsive. And please replay this episode again in case you missed anything, since Yarden tend to make everything like cryptography. So with that, you have to just repeat it twice. So don't forget to follow us on Twitter and at Cyber Riddler, or follow me directly at Al Murabi, and I will be putting Yarden Twitter handle on the link below. And thank you, and I'll see you all in the next episode. Thank you, Yarden.
Thank you very much.
Thanks.